Hello everyone. From today's video, we are going to start to discuss about inverse Laplace transform. Okay, so these are the general formulas or expressions you can say uh, of your inverse Laplace transform of elemental functions. Uh, Here, first one is your Laplace transform of 1. We know that 1 by s, so obviously inverse Laplace transform of 1 by s is equal to 1. So inverse Laplace transform of 1 by s equal to 1. Laplace transform of t, 1 by a square. So corresponding inverse Laplace transform of 1 by a square equal to t. T to the power n, Laplace transform n factorial by s to the power n plus 1. So inverse Laplace transform of this one will be equal to t to the power n. Here you can see, if I am going to put t equal to 1, then this will be 1 factorial means 1, here s to the power 2. So here t equal to 1 means only t. Okay, so these two uh, expressions or formulas you can easily remember if you are going to remember only 3. So if I am going to remember only 3 expression, then I can found 2. Okay, now fourth one is your Laplace transform of a constant. K is a constant. We know that K by S. That implies Laplace inverse Laplace transform of K by S will be equal to K. See here, for 1 equal to 1 by S and corresponding inverse Laplace will be 1. So if K another constant will be multiplied, so obviously the answer will be that constant here K. Okay. Next, fifth one, Laplace transform of e to the at is equal to 1 by s minus a. Inverse Laplace transform will be e to the at. See, these elemental functions already we have been discussed in our first lecture in detail. We proved all the elemental functions Laplace transform. We already proved this one. Laplace transform of some elemental functions. These elemental functions Laplace transform we have been proved. I'm going to show you that fifth one is your e to the power at, Laplace transform of e to the at equal to 1 by s minus a. We proved. Then sixth one is your Laplace transform of sin at will be equal to a by a square plus a square, cos at s by a square plus a square. Each and every elemental functions Laplace transform we have been derived or proved. Only I written the formulas of those elemental functions in the form of inverse Laplace transform. Laplace transform of sin at equal to a by a square plus a square. Inverse Laplace transform of a by a square plus a square equal to sin at. Cos at Laplace transform s by a square plus a square. So you can remember easily that for sin is your a, for cos equal to s. S by a square plus a square, inverse will be cos at. Sin h at a by a square plus a square. See, if I am going to consider this sixth one, sin at and sin ht, here a is there but plus sign is there, a square plus a square, but hat minus is there, a by a square minus a square. So inverse Laplace transform of this one will be sin hat. For cos hat will be s by a square minus a square. Inverse Laplace transform will be cos hat. Now, tenth one is your Laplace transform of e to the power at sin omega t. These things also we have been proved or derived that omega by s minus a square plus omega square, and corresponding inverse Laplace transform will be this one, e to the at sin omega t. E to the at cos omega t will be this one. Inverse Laplace transform will be e to the at cos omega t. E to the at into t will be 1 by s minus a square. Inverse Laplace transform of 1 by s minus a square equal to e to the at into t. E to the at sin h bt, that will be your Laplace transform will be b by s minus a square minus b square. Inverse Laplace transform will be e to the at into sin h bt. Laplace transform of e to the at cos h bt will be equal to s minus a whole divided by s minus a square minus b square That implies inverse Laplace transform of this one will be e to the power at into cos h bt. Laplace transform of t sin at equal to 2as by a square plus a square whole square equal to inverse Laplace transform of this one will be t sin at. Laplace transform of t cos at equal to sin a square minus a square by a square plus a square whole square. So corresponding inverse Laplace transform will be this one, t cos at. So this 10th, 11th, 12th, 13th, 14th elementary functions and corresponding Laplace transform I just kept in a box. Why? These are can be remembered by considering shifting theorem. Here I am going to explain. E to the power at equal to 1 by s minus a. So according to your first shifting theorem is telling that e to the power at into f of t equal to capital F of s minus a. Here capital F of s is your Laplace transform of f of t. So whatever the Laplace transform of f of t we have or we know, if e to the power at has been multiplied, the Laplace transform will be only wherever s will be there we are going to consider s minus a. That already we know. First shifting theorem I am going to show you. First shifting theorem, here you can see this one, okay. E to the power at f of t equal to capital F of s minus a. So here you can see that e to the power at sin omega t. Sin omega t, if I am going to consider sin omega t, what will be Laplace transform? Laplace transform will be omega by a square plus omega square, because we know that sin at is equal to a by a square plus a square. So omega t will be omega by a square plus omega square, a square plus omega square. If e to the power at has been multiplied with sin omega t, then the Laplace transform will be omega by, according to first shifting theorem, s minus a. So this is the Laplace transform of sin omega t. So e to the power at means wherever the s, there we are going to consider s minus a square plus omega square, right? So easily we can remember, if we remember these elementary functions and its corresponding Laplace transforms, then 10th, 11th, 12th, 13th, 14th expressions no need to remember. You can easily write. So e to the power at cos omega t, cos at s by a square plus a square. So e to the power at cos omega t means here s minus a, here s will be s minus a, here s will be s minus a square. So as this is your cos omega t, so s minus a square plus omega square. E to the power at t, see, for the t this is 1 by s square. E to the power at means s minus a square. Likewise e to the power at sin h bt, sin h bt is your a by a square minus a square. So sin h bt, if you are going to consider, then it will be by sin b by a square minus b square, but e to the power at is there. So b by s minus a square minus b square. Likewise e to the power at in cos h bt, you can remember. So this is all about inverse Laplace transform of the elementary functions, 16 elementary functions. I suggest that you have to remember all the Laplace transforms of these elementary functions, which are most essential for solving the numericals. So here you can see, if you are going to remember this one, then you can, no need to remember this one. If you remember for the constant, no need to remember this one, okay. So these 1 2 3 4 5 no need to remember if you remember this much, okay. If you remember this much, no need to remember. So here another one, e to the power at is there. So Laplace transform of, suppose e to the power bt into e to the at will be there. For e to the at is nothing but 1 by s minus a. Here bt means 1 by s minus b minus a. So a will be answered by using the fast shifting theorem. So this is your using fast shifting theorem. Fast shifting theorem, these five expressions we can extract easily. Thank you so much for watching this video. And next class we are going to discuss properties of inverse Laplace transform and corresponding numericals. Once again, I am going to suggest to all of you that remember in Laplace transform of these 16 elementary functions, which is most essential to solve the numericals. Thank you so much for watching this video. Thank you.